One
Go ahead.
second.
Thank you.
Let me just pull up the chat from Zoom. I think once I share, it's not that visible.
Yeah. I can ask you the question too.
Okay, I can see that now. Yeah, all right. Okay. All right. Thank you everyone for having me here. My name is Urmish Thakker, and I'm a principal engineer at Sambanwa Systems. Today, I'll be talking about some of the software hardware innovations that we have been doing to develop an efficient training systems for training deep learning algorithms. So before I get deeper into the technical side of the talk, I wanted to introduce the concept of Goldilocks zone. So Earth lives in a zone that is dubbed as the Goldilocks zone. What that means is that if we would have been closer to the sun, then the climate at Earth would have been too hot for us to sustain life. And if we would have been slightly away from the sun, the climate on Earth would have been too cold to sustain life. Now, the reason I sort of brought up this analogy of Goldilocks zone is because we at Sambanwa Systems believe that when it comes to deep learning models, we are stuck in a Goldilocks zone. Models that work well and are sort of execute well on GPU architecture are the models that get adopted, both from a production point of view and also from a research point of view. And models that don't really fit well into the GPU architectures might not get as well adopted or might not get consumed from the other research community, even though they might be providing value. And these models do provide value. If I look at the left side and the right side of the Goldilocks zone, both of these kinds of models do provide immense value to the customer and the end user. On the left side of the Goldilocks zones are these extremely small and narrow models. These models allow you to have extremely fast inference runtime while achieving 90 to 95% of the accuracy from the models which they are derived. Now, latency is important for a lot of applications like, say, search queries or chatbot applications. On the right side of the Goldilocks zone are these models that are extremely large. Think about the largest language model that you can think of. These models are tending to trillions of parameters and don't really fit within the narrow memory budget that GPU has to offer. These large language models have shown immense capabilities in improving the accuracy that was previously possible, and have also added significant value to the end customers and the users by providing capabilities like zero-shot learning and few-shot learning. These capabilities allows these language models to be adapted to a wide variety of applications with minimal effort or engineering or sort of minimal effort or research required. However, these large language models are difficult to run inference on or train on, and thus a new kind of model or no new kind of hardware is required to rethink deploying these large language models. Now, with these restrictions in mind, the mission at Sambanwa Systems is to shape the next generation of deep learning computing systems to accelerate the full model spectrum. We are not just concerned with the Goldilocks zones that the GPUs support, but we are looking at all kinds of applications, both from the smallest models to the largest of language models. We believe the only way to sort of achieve this goal is to fundamentally reinvent different layers of the stack, from hardware, compiler, to all the way to algorithms, allowing us to rethink or redesign models that achieve good accuracy for the end application. So in this talk, I'll go over some of these innovations. I'll talk about the innovations that we have made on the hardware side of things, followed by compiler. And then I'll talk about how the algorithm innovations complement our hardware in order to achieve the high efficiency deep learning systems that I've been talking about. Eventually, I'll talk about some of the models and use cases that we are the only company able to support, and why this is happening and how they are enabling state-of-the-art accuracy, which was not previously possible. All right, so let's start from the hardware side of things. At the core of our systems is the reconfigurable data flow unit. The reconfigurable data flow unit is you can think of it as an sort of a array of compute, where each compute unit has its own local SRAM, and this array of compute is interconnected by, or it is connected by a complex interconnect fabric. This reconfigurable data flow unit is built grounds up to execute data flow graphs. Now, Currently, the data flow graphs that you see in deep learning algorithms are executed on a GPU in a kernel by kernel fashion. What that means is that each operation in a graph is executed one time step at a time on a GPU. Every time you switch from one operation to another, you incur what is called as the kernel launch latency, and you incur also the latency to read values from the DRAM for the inputs that are required for the current operation to execute on the GPU from the DRAM. However, the data flow graph that neural network generates can be executed in a fundamentally different way, and this is what the RDU is built for. We execute the data flow graph spatially, and our hardware is designed to exploit parallelism that exists naturally in these data flow graphs. If what I said previously was not clear, hopefully this slide and this figure will make it a bit more clearer. So here what you see on your screen is a two-layer neural network. This neural network consists of two convolution layers followed by a normalization and a summation layer. Now, on a GPU, this neural network would have been executed one operation at a time. So you would have your convolution operation executing first, then your pooling, and so on. However, with the compute capabilities that the RDU offers, we can actually map this entire graph onto our hardware spatially and execute all of these layers in a more efficient manner. What we do currently right now is that we map all of these layers onto this hardware such that we read in the weights required for each of those layers within the local storage of those compute units and connect different layers using the interconnect fabric that we have. During execution, we input the required data into the accelerator and allow it to flow through the accelerator. So first, the input passes to the first layer. The first layer already has its weights in the local SRAM storage. It reads those local SRAM storage, reads the input, and then creates partial input, which are then, or creates activations, which are then passed on to the next layer using the interconnect fabric. While previously on a GPU, you had latencies associated with launching a kernel and reading the inputs from a DRAM. In this case, you can see that there is no kernel launch latency associated, nor do we have to go to DRAM to read the inputs. Everything remains on the substrate or on the compute substrate that we have. And because the data flows through the graph and to the final endpoint, we really don't have to go to DRAM to fetch any of the values required. Overall, this allows us to achieve really high efficiency when we are executing the neural network on our hardware. Now, achieving spatial data flow on our hardware is not easy. It requires really good compilers that can map a particular data flow graph in an efficient manner. So what you see on the screen on the left-hand side is a typical data flow graph that you see in a neural network algorithm. This data flow graph consists of the forward operations, the backward operations, and also the optimizer steps. As you can see, these data flow graphs can get extremely complicated. A naive compiler, when mapping this onto a hardware, can create communication patterns that you see at the top of the screen. These zigzag kind of communication patterns end up using way too many resources in terms of transferring data from one compute unit to the other, almost killing the performance that can be possible on our hardware. But folks at Savannah Systems have pioneered a new kind of a compiler that allows us to map these algorithms onto our hardware quite easily. And you can see some of the work that our compiler can do in creating a spatial outmap that is much more cleaner and creates better utilization and faster execution.
Urmish, there's a question on the chat.
Sorry. Oh, yeah. How do these architectures scale to problems that are just slightly larger than can be really mapped to the hardware? See the program may be batched as well. Right. So if we have a sort of an architecture that is larger than what can fit onto an RDU architecture, the way we execute is what we call as a section by section execution. We'll try to map as much of the graph that we can onto our hardware and then sort of make a section cut at that point of a graph. And then sort of the next part of the graph is then mapped onto the next section. And these sections are then executed one time step at a time, right? So we are still reducing a lot of the kernel launch latency because we are mapping at least a lot of different layers onto our graphs simultaneously. And when for the graphs that are mapped onto our hardware, the data is also flowing within our hardware and not going to the DRAM. I hope that answers your question. Okay. So moving on. So if one has to think about how do we think about a data flow based hardware that Sambhava system is pioneering, this graph would be a good way to sort of visualize it. What we are plotting on this graph is energy efficiency on the y-axis and a notion of reprogrammability on the x-axis. On the left-hand side of this particular graph are your ASICs or fixed function accelerators. Now, these fixed function accelerators are extremely energy efficient, but also are not reprogrammable. For new applications or sort of new way of doing algorithms for the same set of applications, you have to recreate your ASICs, which can be costly. On the rightmost side of the graph are the CPUs and the GPUs, which are easy to reprogram, but are also not as energy efficient as one would like them to be. FPGAs are a good trade-off between them, but RDUs that we are pioneering provide an even better trade-off than what FPGA can provide, in that we are more energy efficient than FPGA while being faster to reprogram. So these were all, so sort of the previous slide introduced some of the hardware and the compilers, introduced some of the advancements in the hardware and the compiler stack that we have been leading at Sambhava systems. I want to also talk about some of the algorithmic innovations that complement these hardware and software, hardware and compiler innovations, and allow our hardware team to aim for more efficient hardware for the next generation of the systems. Specifically, two projects that I would like to talk about are enabling pure 16-bit training and also asynchronous pipeline parallelization. Now, conventional model training algorithms generally use 32-bit precision for number representation. To enable better system efficiency for training deep learning models, there has been a recent trend to focus on low precision training. There has been a plethora of work in low precision training where each work targets a specific architecture or a specific application. These papers are able to solve this issue for a specific niche application or a specific architecture and achieve similar accuracy as a full precision training might have achieved. Overall, this is a very interesting research trend because low precision training has significant advantage. In a true low precision training regime, we can create compute units and we can create a hardware that is only developed to take in input which are at a lower precision and to compute outputs at a lower precision. Overall, this reduces the area of your ALU units and the data paths that you have within your accelerator. Effectively, this can help us achieve almost 1.5x lower chip area, 3x higher energy efficiency, and 1.5x higher throughput. The overall energy efficiency in the chip area that you gain, you can in fact use them to store in more compute units, or you can use them any way you like, giving you more flexibility in order to make your systems better at deep learning training. However, the generalized packages that are generally available for low precision training create an illusion of low precision training. These packages that people generally tend to use work well for a wide variety of applications and hence have found significant adoption amongst the deep learning community. However, these packages also suffer from the problem that instead of doing low precision training, what they do is mixed precision training. What that means is that for all weight values in the graph, they also maintain a 32-bit weight copy in the memory, apart from the 16-bit weight copy that exists. Now, the forward and the backward part of the graphs are executed using the 16-bit precision values of the weight. However, the optimizer section is generally executed using the 32-bit precision values of the weight. Also, depending on the model, sometimes some of the activations in the middle of the layers might also be 32-bit precision. As a result, you can only execute these algorithms on a hardware that supports both 16-bit precision and 32-bit precision ALUs. Given that 32-bit precision unit ALUs also have an important role to play, you do not gain the same efficiency as we talked about previously. So the question that we asked ourselves at Sambanova Systems is that, can we get away by only designing an accelerator that only supports 16-bit computations? And when we do that, will we be achieving the same model accuracy that you achieve using 32-bit training? To understand this, we dug a little deeper as to where exactly these issues can be arising from and how can we fix them. Now, a training graph generally has this particular data flow that you see on the left-hand screen. If it's a 16-bit training, what you will have is 16-bit weights. Once the input passes through this graph, these 16-bit weights would generate activations which are going to be 16-bit. Eventually, the activations and the weights would be used to generate gradients which are going to be 16 bits. And after the optimizer steps, the gradients are going to be used to create the updated weight values, which are also going to be 16-bit. If I look at the multiply accumulate units within this particular, within the training, multiply accumulates, which are the workhorse of any deep learning training algorithm, this is what it would sort of look like from a precision point of view. Your multipliers would be taking in 16-bit inputs, and they would be accumulating until you reach the end of your array. These accumulation would generally be happening at a higher precision. And once the accumulation step is over, we'll be back to the 16-bit precision value that we want for our weight value. Now, typically, most hardwares that are around look at using nearest neighbor rounding or getting from 32-bit precision to 16-bit precision. So given that everything else is happening at the resolution that we want, we think that the primary source of numerical error that leads to instabilities during low precision training is coming from the usage of these nearest neighbor rounding algorithms. If we do pure 16-bit training and compare applications that are applications versus the 32-bit training regime counterpart, we see that there is a huge accuracy difference. In this case, I'm plotting the accuracy versus plotting this accuracy as the training progresses for a BERT MNLI, which is in a natural language processing application. As you can see, over time, the 16-bit training curve saturates much before than the 32-bit training curve, effectively creating a huge gap in the in the final training accuracy. Now, just looking at this particular graph, one might seem to believe that pure 16-bit training regime does not work. And we will in fact need the mixed precision training regime to get to the accuracy that we want. However, that's not actually true. The main reason 16-bit training regime does not get to the accuracy that we want is because of nearest neighbor rounding. To understand why that's happening, let's look at how weight updates happen in a neural network. You feed in a mini batch into your neural network. That mini batch you calculate the loss based on that particular mini batch. Based on that loss value, you calculate your gradients. Once you have your gradients, you update your weight values using a favorite optimizer. Suppose your optimizer that you're using is a simple stochastic gradient descent. Then your updated weight value is going to be the current weight value minus your learning rate into whatever gradients that you have calculated. Once you sort of get the updated weight value, because you need to be within the 16-bit precision regime, you do nearest neighbor rounding to get to the precision that you want. Now, the problem with sort of nearest neighbor rounding is the fact that you might lose smaller weight updates. To understand what's happening, I think you need to focus on this particular figure that you see on the bottom right corner. Low precision implies that not all of the values that you want on a real axis are available for you to use. You are in fact quantizing a real axis into 2⁻16 different buckets for a 16-bit precision values. So values that don't exactly fall onto the precise quantization values are then rounded to that particular, to the nearest quantization bin using nearest neighbor rounding. So in this case, what you're seeing is that the weight value after update wants to be somewhere between two quantization bins, but because quantization sort of forces that we have to take one of these orange values, nearest neighbor rounding forces these values to go back to the previous value. Effectively, what has happened is that we were trying to update our weights using our current mini batch, but we have lost all of the information that we are receiving from this particular mini batch. And this becomes an extremely important problem because you are sort of facing what is called the model weights, what is called as the halting problem, where your model weights are trying to update, but you are never able to update because of the precision restriction that you have imposed on this particular model. In fact, we can sort of analyze this halting behavior from a theoretical point of view. And once you do that, you can actually tie down the accuracy loss that you see to the nearest neighbor rounding quantization that we are currently doing in low precision training. So the question becomes, how do we fix that? And fixing that is important because once you do fix that, you get into a hardware space where you only need to support 16-bit compute units. So we explored two different ways of fixing this method. One was stochastic rounding, and the other was Kahan summation. Both of these methods are simple and have been very effective. Stochastic rounding is sort of introducing a noise into the nearest neighbor rounding process. What that means is that we'll be doing nearest neighbor rounding with some probability, but every now and then, when the weight update is small, instead of going to the nearest neighbor quantization bin, we might get quick to the next quantization bin. As a result, not all of the gradients are always lost. Every now and then, we are learning enough from a gradient signal to compensate for the nearest neighbor rounding loss that we are seeing previously. In fact, if you take the expectations of the gradients which have been created using nearest neighbor, using stochastic rounding, we actually get unbiased estimates of the actual gradient value. And unbiased estimates is a very important property. Which is needed to ensure or to provide guarantees that a particular training algorithm is going to work and then get you to the accuracy that you, or the minima that you want. The second form of optimization that we sort of tried out in order to improve the accuracy of pure 16-bit regime was called as Kahan summation. In a way, Kahan summation is a methodology to track the errors that exist after nearest neighbor rounding. Once you add a small update to your weight and do your nearest neighbor rounding, you calculate your error that you have incurred using 16-bit precision. Once you get your error value, you use this error value and compensate for it in the next iteration. Note, all of the computations here are in 16-bit and you're calculating the error also in 16-bit. In a way, what you are doing is, because you're always sort of compensating for the errors that have happened previously, you're keeping a track of the loss of information, and you're trying to ensure that this loss in information doesn't have a negative impact on your accuracy. In an ideal scenario, all of the errors that you have incurred after your nearest neighbor rounding can be compensated for in the next update step. So effectively, both of these techniques, stochastic rounding and Kahan summation, can in theory help you achieve true 16-bit precision training and achieve the same accuracy that you would achieve using 32-bit precision training. So now let us look at some of the results that we have achieved using these two techniques and compare them from the previous results. Here we plot the graph for 3 different applications across the computer vision domain, the recommendation domain, and the NLP domain. In all 3 cases, we are plotting the accuracy, and we are plotting those accuracy, or either the accuracy or some notion of accuracy, depending on the application that we have. For all of these 3 graphs, we are plotting the accuracy across time. And as you can see, if we are doing pure 16-bit training, which is the green curve, and compare that with pure 32-bit training, the green curve never matches the 32-bit training and isn't even close to where we want to be. However, if we either add stochastic rounding or Kahan summation to our 16-bit training regime, then both of these different techniques are able to achieve or able to help us to get to the same accuracy that we want. That is the accuracy that we achieve after 32-bit training. So effectively, we have found 2 different techniques that allows us to do pure 16-bit training and allows us to get the goodness from hardware that a 16-bit compute unit can provide. Both of those techniques have their own trade-offs. Kahan summation has the issue where you need to maintain additional 16-bit copies of your weight every now and for all the different layers in your graph. You may be able to further optimize it by choosing what particular layers of the graph need those 16-bit weights and what not, and what layers do not. But effectively, you can choose one of these techniques to get into the regime where you can actually achieve 16-bit true 16-bit precision training. The second optimization that we explored from an algorithm point of view to increase utilization on our hardware is asynchronous model parallelism. Now, model parallelism is a standard method for training models when they become extremely large that they don't fit onto a compute unit that you have on your hardware. Imagine a graph being executed. Imagine a large language model being executing on a GPU, say. Now, that large language model would not fit on a GPU. So the way you would do that, sort of achieve training on that particular graph, is to break that large graph into multiple smaller graphs, and then sort of map each part of the small graph on one GPU hardware. In this case, I'm sort of showing an example where we have 4 compute units, and a graph is mapped across 4 different compute units. During forward execution, the data flows through all of those compute units. Your input goes to the first part of the graph, which would be on, say, in this case, compute unit 0. You calculate the activations and communicate those activations to the second part of the graph, which is here compute unit 1. Similarly, go to the similarly go to the third compute unit and the fourth compute unit. Once you have gone to the forward parts of the graph, you calculate your loss value and start your backward section or the backward part of the graph. The backward flow starts from the last compute unit, and all of those partial gradients are sort of communicated backwards one step at a time until you get to the last compute unit or the first compute unit, where you calculate the backward path for the first part of the graph. Eventually, you hit a synchronization barrier, and at this synchronization barrier, all of the compute units are expected to update their weight values to get the updated weights for the graphs that can be consumed by the next batch of the input. Now, as you can see, this kind of execution leads to a lot of gap in terms of the compute units being not used as much as we would like them to be used. One form of optimization that people have found is to break a batch into multiple mini batches and feed these mini batches parallelly to ensure that multiple stages of the mini batch are executed across multiple compute units, allowing for better utilization. However, we are still going to hit that synchronization barrier that you see here because the weights still need to be updated in a synchronized manner. So even though we are better than what we had seen previously, the micro batches still introduces some bubbles where some of the compute units are not utilizing, are not doing any work while they're waiting for the synchronization barrier to hit, or they're waiting for their backward signals to be arriving. Note that depending on how far away the compute unit is from the final part of the graph, the amount of time spent in the idle state is going to differ. The compute unit closest to the graph is going to have the least amount of idle time spent, and the compute unit farthest away from the end of the graph is going to have the highest amount of idle time spent. So even though microbatching helps alleviate this issue, you still see this issue of having some gap during execution. Now, in conventional processor pipeline, as the number of pipeline stages increases, the throughput increases significantly. However, on this kind of a training setup where you have a synchronization barrier that you need to hit, as the number of pipeline stages increases, the utilization actually decreases. On our hardware, where you have a significant number of compute units that exist, this utilization can become a problem, and that's something that we wanted to see if we can solve. So the reason we are hitting this simple sort of utilization issue is because we are waiting for these synchronization barriers to hit, or we are waiting for the backward signal to come before we can take our next step. Effectively, once the forward part of the graph is executed, we do not feed the next mini batch required for the training and wait for the backward signals and the synchronization barrier before we start consuming the next set of data. So the question that we asked ourselves is that, can we do away with that synchronization barrier? And can we do away with that sort of locks that we have established on our hardware? And so the idea that we had was that If we can keep feeding data into our hardware and not wait for the backward signals or the synchronization barrier, we could effectively achieve 100% utilization. However, sort of feeding input data without waiting for updated weights or the backward signal creates a very chaotic training regime. Each compute unit in effect would be working on a different set of updated weight values. You can imagine an x-axis which is incrementing, where each incremented value sort of points to the updated or the next time step of the weight values. Ideally, what happens is that all of the compute units gets the updated weight values simultaneously. But in an asynchronous fashion, the compute units are each operating at a different time step on that particular x-axis. What that means is that some compute units would be operating at the older copy of the weights, while some compute units would be operating at the newer copy of the weights. So as the data flows through this pipeline, the data is actually experiencing different versions of the graph at different times. The compute units that are closest to the synchronization barrier or the loss function have the most updated weight copies, while the compute units that are away from the synchronization barrier have the most stalest version of the weight copies. Now, given this chaotic training sort of dynamics where different parts of the graph or different compute units are sort of executing different versions of the weight copies, you can imagine that training becomes difficult to do. Indeed, when we train with such a chaotic asynchronous version of model parallelism, we are actually not able to achieve any better accuracy than random training. In this case, we are plotting the training accuracy versus epoch, that is as training progresses, for a ResNet 50 trained on a simple dataset like CFAR10. And as you can see, the synchronized version of doing model parallelism gives you the accuracy that you want, while the naive version of doing things gives you only 10% accuracy, which isn't better than random guess. So even though you are getting 100% utilization because you keep feeding the micro batches to your compute units, and because you're not waiting for the synchronization barrier, you're not getting the accuracy that you want, so that these attained high throughput does not translate to any useful application. So the question that we asked ourselves is that, can we do better? And the way we sort of achieve this objective is to do learning gate scaling. In the later parts of the compute units, which are closer to the graph, we know that these values, the weight values that you see in those compute units, are going to be more fresher than the previous compute units in the earlier part of the graph. So in a way, the hypothesis that we came up with is that if the learning rate is proportional to how close you are to the synchronization barrier, then maybe you can achieve a better training dynamics than what you have seen on the screen. The intuition there is that the closer you are to the synchronization barrier, the more confident you are in the gradient update step that you are taking. The farther away you are from the barrier, the more difficult it is for you to be sure that the gradient update step that you are taking is less noisy. Effectively, when we do a learning rate scaling regime that I sort of laid down previously, we are able to actually achieve the same or similar training curves that we had seen, equivalent or similar training curves equivalent to what we had seen for a synchronized model parallel technique. For two different applications, we are able to achieve close to 100% throughput and achieve the same accuracy that we expect from a normal model parallel laid out model. So effectively, I talked about two different algorithms that sort of complement our hardware in allowing us to achieve, allowing us to design hardware that are more efficient and also achieve better utilization onto our hardware. Both of these techniques effectively allows us to execute models in a very efficient manner. The compiler that we have developed, because it works automatically, allows us to also map arbitrary graphs that can be arbitrary graphs easily without requiring manual input. Because we have a data flow graph that hides the latency of data, that sort of tries to keep all of the activations onto our hardware, we are also able to hide the latency that might arise from DRAM lookup. This allows us to couple our hardware with a large terabyte of DRAM memory without using simple off-the-shelf DRAM that is currently available. All of these different design points allows us to execute models that in a more efficient manner than what is possible on GPU, or allows us to execute models that are not previously possible to be executed on a GPU hardware. So let me walk you through a couple of examples. Let me start with the computer vision domain. Now, a lot of a lot of computer vision tasks that we have seen and have been successful operate on images that are at a lower resolution. However, over the years, our camera capturing or image capturing subsystems have improved significantly. Also, these camera systems have become cheaper and storage have also become cheaper. What that means is that we are in a new era where most of the images are at a significant higher resolution. These higher resolution images have significant advantage in the AR/VR domain and also in domains like autonomous driving, where you are trying to make extremely critical decisions about navigations on road. Sort of image capturing systems in the medical domain have also improved significantly, and we are talking about now resolutions of the order of 50K cross 50K. Now our resolutions have improved, but our deep learning models that operate or that need to convert this data into some form of intelligence have not. They still operate on lower resolution images. The reason they operate on lower resolution images is because high resolution images creates activation maps that are quite large. And because these activation maps get quite large, they don't fit within the memory, that limited memory that GPUs have to offer. So effectively, while your image subsystems are improving, the models that need to learn from them are not. Now, generally, the way people try to compensate for that is using either sort of projecting a higher resolution image onto a lower resolution space or using what is called as patching. In case of patching, you take a larger image and divide it into smaller pieces and then feed those smaller pieces in some form into your GPU while accumulating your activations in some form or the other in order to ensure that your activation map does not increase significantly. Now, while it might look like a good idea, patching almost breaks an image into multiple pieces and you do lose out on the context of what the image meant. An image has a lot of context in terms of both spatial, in terms of a lot of spatial locality, and patching has a tendency to lose that kind of an information. In fact, we have shown with our collaboration with the Argonne National Lab that if we move away from this patch-based way of doing things or tile-based way of doing things, and then move to a system that can process this high-resolution images effectively, then we can achieve extremely high accuracy, almost 6% more than what was previously possible. 6% more accuracy is a huge upstep in terms of the value addition to an application. And all of this is possible because we have a large DRAM memory and we have a compiler that can automatically take care of all of these inputs without having to worry about doing things like patching or tiling. We show a similar value add when we move towards a more medical specific application. In this case, our collaboration with professors at Harvard has shown that for a cancer detection algorithm, we are again able to achieve significant higher accuracy, almost 6% more higher accuracy than what was previously possible. This notion of higher DRAM corresponding to more accuracy and efficient execution exists in the recommender domain also. In case of recommender models, what you effectively have is large embedding tables, which represents your users or items in some way. You look up these multiple large embedding tables, and to create embeddings that sort of describe your users or items in a vectorized format, then you do a lightweight neural network on top of it to gather the intelligence or get the predictions that you want. Our work has shown that as the size of these embedding tables increases, the accuracy increases. In fact, we are able to achieve 0.4% more accuracy than the previous state-of-the-art model. And we are able to achieve these accuracies much faster because of the data flow computing that we have. Now you might question, is 0.4% accuracy really important? And in fact, every 0.1% accuracy improvement in the recommendation model turns into millions and millions of dollars in revenue. So yes, 0.4% accuracy, while might seem less, is actually extremely important. And a lot of these internet services companies strive for improving recommendation models by 0.1% every year. So by just switching to a hardware that can support large memory and data flow graph, you can create models that are much larger and get higher accuracy at a much faster pace. Our hardware also allows us to innovate on the NLP side of things, both on the small NLP models and the large NLP models. I'm very sure you have been using a lot of small NLP models in your day-to-day life. When you're doing NLP queries or interacting with your favorite chatbot models, you're actually using a small NLP model that is targeted for inference latency. These small NLP models, or some small versions of BERT, generally operate on smaller sequence lengths. Whenever we execute these things on GPU, because of the kernel by kernel execution mode, these models actually don't really execute well on our hardware or on GPU. However, when we sort of execute them on our hardware, we can actually map some of these models directly onto our hardware, and the spatial data flow execution allows us to achieve much better efficiency than what was previously possible. In fact, if I look at TinyBird and sort of compare for different sequence length, we are able to achieve inference latency that can be anywhere from 3.4x to 11.1x better than what was possible on a GPU. It's not just small models where RDUs can be useful. For language models also, they are extremely useful. Language models are sort of a special kind of applications that do things in two different phases. First is the pre-training phase, and the second is the fine-tuning phase. Pre-training phase is where you sort of do weeks-long training or sometimes month-long training to learn that whatever you can from the data that you have available on the internet. Once you learn everything you can from the internet, you sort of specialize that application for the task that you might want. A lot of times these language models are actually specialized for each domains like legal, medical, finance. And for all of these domains to sort of pre-train on a large corpus that a company might have. So improving this training sort of turnaround time of pre-training is extremely important because these pre-training times could be in weeks or months, and any efficiency gain that you can achieve can cut down experiment times from weeks. These language models are also increasing in size. In fact, scaling laws have shown that as the language models get bigger and bigger, the number of applications that you can enable are also sort of rising exponentially. In fact, with these large language models, the specializing and fine-tuning phase can completely become irrelevant, and you have discovered a new way of deploying these applications. We at Samanova Systems are very much aware of these trends and have created a system that can run these large language models extremely efficiently. We are looking at an inference latency and inference throughput that is significantly higher than A100. And for these large language models to the tune of 1.2 billion and 13 billion, we are able to cut training time by weeks. We are currently training a 13 billion model and are also setting up to train a 175 billion language model. So this is all I had at my end to sort of introduce all the hardware and software innovations that we are doing at Samanova Systems and how they help us achieve a new kind of, run new kinds of models or existing models significantly faster. I hope you learned something from this presentation and are excited about the hardware that we are building as much as I am. Thank you.